You ever stop and think about how all of our smart stuff actually talks to each other? I mean, your smartwatch, a traffic light halfway across the city, and some random sensor on a farm? How do they all connect to the internet? It seems like it should just work, but it's way more complicated than you'd think. Today, we're going to pull back the curtain on this hidden world of IoT communication. And yeah, this is a massive, massive challenge. We're not just talking about a handful of gadgets in your home. We're talking about billions of devices. A lot of them are in really remote places, and they all need to sip power, not guzzle it down like our smartphones do. So how on earth does this giant global conversation actually happen? Okay, you might be wondering, why can't these little sensors just act like tiny smartphones? Well, it turns out they're playing a completely different ballgame. They face some really unique obstacles that have required some incredibly clever solutions to get around. It really boils down to four big hurdles. First off, these devices are built to be small and cheap, so they have very little processing power and tiny batteries. Second, the scale is just mind-boggling. Trying to manage billions of connections is a huge task. Then you've got the fact they have to survive in really harsh environments, everything from deep underground mines to remote forests. And finally, the networks they use are often lossy, which is just a fancy way of saying data can easily get dropped or lost along the way. So how do engineers even begin to tackle this? Well, they start with the most basic thing, the layout. It's what we call the network topology. You can think of it like the architectural blueprint for the whole system. And in the world of IoT, two designs are everywhere: star and mesh. First up is the star topology. It's really simple and elegant. Every single sensor or node talks directly to one central gateway. Think of it like the spokes on a bicycle wheel. Everything connects to the middle. There's no crosstalk between the sensors themselves. All communication has to go through that central hub. And then you have the mesh topology. Now, this is more like a web or a net. Here, devices can talk directly to each other. So if one sensor is too far away from the main gateway, no problem. It just hops its message to a neighbor, and that neighbor relays it forward, creating this really resilient, interconnected network. So, as you can probably guess, this leads to some major trade-offs. A star network is super power efficient and pretty secure, but it has one critical weakness. If that central hub fails, the entire network goes down. Ouch. A mesh network, on the other hand, is way more robust. It can self-heal by just finding a new path for a message. But all of that hopping and relaying eats up more power. So you see, there's no single best answer. It always depends on what you need it to do. Okay, so once you've picked your layout, the devices need a way to actually understand each other. It's not enough to just be connected. They need a shared language, or what we call in the tech world, a communication protocol. This is what makes sure that a message sent by one gadget can be correctly interpreted by another. Now, there are a lot of these protocols, but we're going to zoom in on one of the most popular, MQTT. And here's a fun fact. It was actually designed way back in the late 90s to monitor oil pipelines. I mean, talk about a harsh environment. It's incredibly lightweight and efficient, which makes it absolutely perfect for those tiny power-sipping devices we've been talking about. The way MQTT works is just brilliant. Think of it like a digital post office. A sensor, which we'll call a publisher, sends a message to a specific topic, let's say home/living room/temperature. But it doesn't send it to another device. It sends it to a central server called the broker. That's our post office. The broker then delivers that message to any other device that has subscribed to that specific topic. The cool part? The devices never even know that the others exist. And MQTT is also really flexible about how reliable you need your messages to be. It offers 3 quality of service levels. QoS 0 is basically fire and forget. You send the message and just hope for the best. QoS 1 guarantees it'll get there at least once, though you might get a few duplicates. And QoS 2 is the gold standard, ensuring the message arrives exactly once, no more, no less. The key is you get to choose the level of reliability that your specific situation actually needs. But this post office model highlights a critical weakness. Because everything, and I mean everything, flows through that central broker, it becomes a single point of failure. If that broker goes down, your entire network just stops working. And that's why in any serious real-world setup, having a backup or what's called a redundant broker is absolutely essential. Okay, so we have the layout and we have the language. But how does the data physically get from point A to point B? I mean, what technology is literally carrying the signal through the air? Let's dive into that. So, wireless tech for IoT pretty much comes in two main flavors. First, you've got the short-range stuff you're probably already familiar with, like Wi-Fi and Zigbee, perfect for a smart home. But then you have the real game changers, low-power, wide-area technologies, or LPWA. And as the name implies, these are designed to send tiny bits of data over huge distances using next to no power. So why are these LPWA networks such a big deal? Well, get this. A staggering 86% of IoT devices use tiny amounts of data. We're talking less than 3 megabytes a month. They don't need a blazing fast 5G connection. They need a hyper-efficient connection that puts battery life and range above everything else. And this is the magic of LPWA. This is what allows a simple sensor running on a little coin-sized battery to keep working for years while sending data over several kilometers. It pulls this off by using special radio frequencies and some really clever tricks to push a signal incredibly far without draining the battery. This technology is what makes things like huge smart farms and sprawling smart cities a reality. So now let's put all the pieces together. Building an IoT network isn't about picking the single best technology. It's about being an architect and choosing the right combination of topology, protocol, and wireless tech for a very specific job. And you can really see how this plays out in practice. For a smart home, right, a self-healing mesh network using a short-range technology like Zigbee makes total sense. But for a smart farm with sensors spread way out, a power-efficient star topology using a long-range LPWA technology like LoRaWAN is the obvious winner. And then in a factory that needs high speed and reliability, you might even use a wired star network with a different protocol, like CoAP. Each one of these use cases demands its own custom-built solution. So from the network's blueprint, to its language, to the tech that carries the message, IoT communication is this fascinating dance of trade-offs. There is no one-size-fits-all solution. It's this careful balancing act that allows our world to get smarter, one tiny packet of data at a time. And it leaves us with one final thought. As billions more devices come online, what new, even more efficient languages will they need to learn to keep this incredible conversation going?